Today we are going to talk about the microwave spectroscopy. So here molecules are classified into four types: linear tops, symmetric top, spherical tops, asymmetric tops. First we'll see the linear tops. So in case of linear tops, let's say we'll take so the molecules which are belongs to C alpha V point group and D alpha H point group, they will comes under this linear tops. We can say carbon dioxide, which is belongs to D alpha H point group, and for this we have this one, carbon sulfate. So molecules which are belongs to the C alpha V point group and D alpha H point group, they comes under the linear tops. So here the main thing we have to identify the relationship between IA, IB and IC, and how many moment of inertia is possible, moment of inertia, and how many microwave active moment of inertias are possible, and these are the things we need to identify here. So here take a molecule carbon dioxide, and here we'll draw the lines, three axes. This is one axis, second axis, third axis. Here this is the principal axis, so always we'll call principal axis as a parallel axis, and this is the perpendicular, this is perpendicular to the principal axis, so we call it as a perpendicular axis. So imagine that this is IA, IB and IC, or we can say A axis, B axis or C axis. See here in the linear molecule, as we know that in linear molecule dipole moment is 0. If dipole moment is 0, moment of inertia also 0. Okay, so here along this axis, this is the linear, along this axis dipole moment is 0. So because of that reason IA will be 0, and along this axis and this axis moment of inertia will not be 0, and both the axes are having equal contribution. Okay, so since along this axis dipole moment is 0, that's why IA equals 0, but along this axis dipole moment cannot be 0 because they are having equal contribution for atoms. So because of that IB is equals to IC. So finally we will write a relationship IA, IB, IC is not equals to IA is not equals to IB and IC. So here we can see that since IA equals 0, this is microwave inactive, and IA, IB and IC not equals to 0, because of that this is microwave active. So they may ask how many moment of inertias are microwave active in case of linear tops. So only one moment of inertia is microwave active because the dipole moment is not equals 0 here, whereas in case of IA this is microwave inactive. So number of moment of inertia is possible here it will be 2, because this is one moment of inertia. Of course this is microwave inactive, but this also we can consider, and this is another moment of inertia, so total we will get 2 moment of inertia here, and microwave active is 1, so this is not microwave active. So this is about the linear tops. So now we'll go for the symmetric top. This is very important, and symmetric tops are further divided into 2 types. So in case of symmetric top, two principal axes moment of inertia is same and one axis moment of inertia is unique. If IA and IB is same, then IC will be either less than this or greater than this. So that's why we call it as a unique. So two moment of inertia is same and another moment of inertia is unique in case of symmetrical top. Okay, so that's why it's very very important. So further, symmetric top classified into two types. One is prolate kind, second one is oblate. So prolate means it's like a cigar, it looks like this, and oblate means this is the shape for oblate. Now we'll see how prolate and oblate moment of inertia will be differ. For prolate molecules, we can take example as a methyl iodide. Okay, so here we have a, this is the shape of the methyl iodide. Okay, and here we have a principal axis, that is C3 axis, and here we have two more axes. This is, imagine this is A axis, B axis and C axis. So here IA is parallel axis and IB and IC are perpendicular axis, because here we have a C3 axis. Always remember CN axis will be parallel, another axis will be perpendicular. So this is along the axis, that's why IA is parallel and IB and IC will be perpendicular. So here in case of C3 axis, so here C3 axis is going through the hydrogen atoms, right? So this hydrogen goes from here to here, and this goes from here to here, and this comes from here to here. So as we know that moment of inertia is directly proportional to the reduced mass, and the C3 axis involves lighter atoms, only hydrogen atoms are involved here. So because of that reason, the moment of inertia which is contributed for the IA axis is very very less as compared to IB and IC. And again I am repeating, the moment of inertia contributes for IA axis is very very less, because here it's a lighter atoms are involved, that is hydrogen atoms are involved. Because of that reason, IA will be very very less compared to IB and IC. So the relationship will be IA is less than IB is equals to IC. This is for the prolate molecules. Okay, and now we'll go for the oblate kind of molecule. Here we can take methyl nitrile also as an example, and we'll go for the oblate. So the best example for oblate is BF3. So here we have a three axis. We will draw all three axes first, so that it will be clear. So this is IA axis, this is IB, and this is IC. Okay, so here we can call IA as parallel and IB and IC as a perpendicular. Okay, so in this case IB and IC are passing through the, means here this is the C3 axis, right? So here in case of oblate molecule, C3 axis involves the fluorine atoms, through the three fluorine atoms and one boron atoms. So whereas IB and IC is not passing through the all fluorine atoms. IB is passing through the one boron and one fluorine, and IC also passing through the one boron and one fluorine, but IA is passing through the one boron and three fluorines. So because of that reason, IA is greater than IB and IC. In case of oblate, IA is greater than IB is equals to IC. It's very simple. Like here in case of prolate molecule, what here is saying that here it's a lighter atoms are involved, so because of that reason IA is less than IB and IC. And whereas here the C3 axis involves boron and fluorine, it's passing through the boron as well as three fluorine atoms, so because of that reason IA is greater and compared to IB and IC. In this case parallel is greater than perpendicular for oblate, whereas for prolate perpendicular is greater than parallel. So this is also another important thing here we need to remember. And in case of symmetrical top, no moment of inertia is zero, so all moment of inertias are microwave active. So here we have two moment of inertias. So here if you take prolate molecule, here we have IA and IB and IC, two moment of inertia, they both are microwave active, and as well as in case of oblate also we have two moment of inertia, they also microwave active. So this is about the symmetrical top, and there are some so in case of symmetrical top, examples are very important. We can take for symmetrical top examples will be D3H point group and D4H point group, D6H point group. This comes under the oblate type. Okay, and sometimes C3V also, C3V that comes for the prolate. Okay, so this is about the symmetric top, and next we'll go for the spherical tops. For spherical tops, the examples will be octahedral, tetrahedral and icosahedral. So all spherical molecules dipole moment is zero. So because of that reason the moment of inertia along three axes will be same, and all are microwave inactive because dipole moment is zero. Because of that reason all molecules are microwave inactive for spherical tops. And next category is asymmetric top. So asymmetric top means along all three directions, axis x, y, z, along all three axes the moment of inertia will be different from each other. So because of that reason Ix is not equals to Iy and it's not equals to Iz. This is the moment of inertia for the asymmetric top molecule. For asymmetric top molecules we have a three different moment of inertia. Along x-axis one kind of moment of inertia, along y-axis different, along z-axis different, means three different moment of inertias we have along the three axes, and all three moment of inertias are microwave active. So they may ask a question that how many microwave active moment of inertias are present for the asymmetric top molecules. So we have three. So for examples for this kind asymmetric top molecules are C3 point group, V shape, T shape, and these comes under the asymmetric top molecules. Like water molecule comes under asymmetric top, and T shape means this kind. This is T shape, and I think Sisa also comes under asymmetric top only. And what else? So these are the examples for the asymmetric tops. And in this topic the main important one is symmetric top and asymmetric top. So asymmetric top examples are very important. They may give one compound, they may ask to find which top it is. So that we need to identify. For symmetric top this moment of inertia is very important. For prolate, as we know that perpendicular is greater than parallel, because the principal axis involve lighter atoms. And for oblate we can take benzene molecules also for oblate, and this is the principal axis for benzene atom, and this is second, and this is third. So here also Ia is greater than Ib and Ic. So all prolate molecules are parallel